Thank you so much, Hiroshi, for the invitation and also for the introduction. And I want to say to everyone that I greatly regret not being in Sendai in person. I look forward very much to strings math in Sendai, but because of a family event, which luckily is a happy one, but still it's made it impossible for me to be present in person, for which I'm very regretful. My topic today, as you can see, is open-closed topological gravity in 2 dimensions. And I'll begin by just reviewing a couple of things about 2-dimensional gravity. So, 2-dimensional gravity is potentially a simpler case than gravity in higher dimensions. And because of that, it was much studied in the 1980s, and several different approaches were developed. So first I'll recall one approach that involves a discrete approximation and the large n limit of a matrix integral. And here I've listed some of the early contributors. So to make a discrete approximation, you can consider, for example, a random triangulation of a 2-manifold with T triangles, where T is going to go to infinity. And then you, for example, think of the triangles as equilateral triangles with a very small length A. And you take T to infinity and little a to 0 with the area of the surface approaching a limit. And you hope that in some sort of limit with little a going to 0 and T to infinity, random triangulations will generate some reasonable model of quantum gravity. Now, so we have to, for this purpose, count triangulations of a fixed 2-manifold. So how to do this was essentially shown over 40 years ago by Hooft. You consider an integral over the matrix elements of an n by n Hermitian matrix M, and then you expand the integral in powers of lambda and 1 over n, and the coefficient of an appropriate power of n and lambda is the number of trivalent graphs with a given number of vertices that can be drawn on a Riemann surface of genus G. And then, as first shown by Brzan and collaborators in 1977, this integral can be effectively analyzed for large n by random matrix methods that go back to earlier authors. Now, what the physicists that I cited at the beginning did was to show that you get a more interesting result if, while taking n to infinity, you also adjust the coupling lambda to a critical value at which the perturbation expansion diverges and the typical number of triangles goes to infinity. In this scaling limit, as I just said, the typical number of triangles diverges, and you get what's believed to be a good model of 2-dimensional gravity. So the model is completely soluble in this limit, and the solution was given almost 30 years ago by 3 groups. Now, that's about as much as I will be able to say for today about this approach. There's a second approach to 2-dimensional gravity, which I'll be able to say even less about. That's a conventional bosonic string with the matter system taken to be a alluvial field with its coupling adjusted so that C is 26. So you replace the 26 bosons of the usual bosonic string with a single alluvial field of C equals 26. So this framework is conceptually interesting and natural. It puts the subject in the framework of string theory. It does not lead in any obvious way to a simple method to calculate, but you can calculate a lot of things that way, and it was found that all the things you can calculate agree perfectly with what you get from the matrix model. So very strong evidence was found in the 80s that the result from this alluvial theory approach is equivalent to what you get from the matrix model. Now, there's a third approach, which was also found in that period to be equivalent to the first two, and that's what I'll be focusing on today. This involves intersection theory on the moduli space of Riemann surfaces. So let MGN be the moduli space of Riemann surfaces sigma of genus G with n marked points or punctures, and I'll label the punctures as x1 up to xn. So in the example you see on the slide, there are 3 punctures. And then at the ith puncture xi, let wi be the cotangent bundle to sigma at that point, xi. As sigma varies in its moduli space, wi varies as the fiber of a complex line bundle Li over the moduli space. Then the correlation functions of two-dimensional topological gravity are the corresponding intersection numbers. So you integrate over mgn, and then for each I, you take the ai'th power of psi sub I, which is also abbreviated, as I've written a little bit below, where tau sub A is short for the 8th power of the first term class. So you write this intersection number as the integral of a product of operators, tau A1 up to tau AM. So these are the basic observables of two-dimensional topological gravity. I should say that technically, by MGN, I always mean the Deligne-Mumford compactification. So MGN, in that sense, is compact-oriented and without boundary, so the integral of a product of cohomology classes, such as the first-term class of psi I, is well-defined. You get simpler results if you take all these intersection numbers and make for them a generating function by summing over G, the genus, and M, the number of mark points, and all choices of the integers AI by which the mark points are labeled, and then you include factors to keep track of all that. So you define a free energy F that depends on infinitely many parameters, the T's, and also on the string coupling constant. And it's a linear combination of all the correlation functions we had before. So the details of this formula are not that important. I even see a misprint because what I defined should have been called e to the f, not f. But the point I wanted to make is that because a mark point can be labeled by tau sub n, the nth power of the first term class, for any non-negative n, a natural generating function that sums over all the choices will depend on an infinite set of variables, namely the string coupling constant, but also parameters t0, t1, and so on, that keep track of how many mark points there are with different labels. So as a physicist, you'd say that the Tn are coupling constants, which are the coefficients with which the operator tau n, or more precisely its two-form gravitational descendant, appears in the action. So I conjectured quite some years ago, in 1990, that intersection theory on moduli space, or topological gravity, is equivalent to the other two approaches. In this correspondence, to simplify a little bit, the intersection number that I defined earlier with a star, this one in the middle of this page, corresponds to the expectation value of the product of traces of the matrix. And you can take the trace of the matrix labeled raised to any integer power. Each integer can occur any number of times. So the matrix correlators depend on the same data as the intersection numbers in the topological description. And the assertion is that the two are in correspondence. So this conjecture was originally proved by Kontsevich in the early 90s, and there are several additional proofs made since then. I won't explain any of these proofs today, but I do want to mention that my recent paper with Robert Dycraft contains an introduction to Mirzakhani's approach. Instead of explaining something about those proofs, I want to tell you about another side of the story. What happens if the surface sigma has a boundary? So in today's lecture, sigma will still be oriented, but it will have a boundary. In the approach based on triangulations of the Riemann surface, there's no problem. There's no difficulty to triangulate a Riemann surface with boundary. So here, I've sketched, well, it's meant to be a Riemann surface with boundary. The boundary is the vertical red line on the left. The Riemann surface is on the right. And I've sketched a triangulation of a Riemann surface with boundary. In particular, the boundary is also triangulated, which simply means it's divided into line segments. And although it's a little more subtle, there's also no problem to find a matrix model that counts triangulations of a Riemann surface with boundary. You simply add to the matrix model degrees of freedom psi and psi bar that are in vectors rather than matrices, and you consider an integral such as the one I've written, where you integrate over m, psi, and psi bar, and then psi bar and psi coupled to the matrix, and also psi and psi bar can be given a bare mass U. Equivalently, you can integrate out psi and psi bar and get an integral for m only. For example, if psi and psi bar are fermions, the result of integrating them out is what I've written with the extra factor of the determinant of m minus u. Now, it's also relatively clear, though a little more subtle, how to include boundaries in the string theory description. You need to find branes in the theory of the C equals 26 Liouville field. A relatively such brane is constructed with Neumann-like boundary conditions, and it has one boundary parameter, the boundary cosmological constant, which is the coefficient in the action of a term proportional to the length of the boundary. And it corresponds to what I called U in the matrix integrals on the previous slide. But what happens in the approach based on intersection theory on moduli space? Well, before I explain what goes wrong, let me explain something nice that happens. If we're going to have a boundary, we presumably want boundary punctures as well as bulk punctures. So in this picture, I've labeled a bulk puncture as x and a boundary puncture as y. Now, the bulk puncture has a tangent bundle, and it has a first Chern class from whose powers we make all those observables we had before. But for the boundary puncture, the tangent bundle is trivial because the tangent vector to the boundary gives a, well, first of all, the boundary, the tangent space of the boundary gives a real subspace which even is oriented, or has a positive direction because the boundary itself is oriented. So the tangent bundle to the surface of a boundary puncture y is actually trivialized topologically. And so there's no analog of those first Chern classes. So there aren't any new cohomology classes to consider when you have a boundary. All we can do is integrate the same cohomology classes we had before, but now we can integrate it over a new moduli space that has n prime boundary punctures as well as n bulk punctures. And let's say it has h boundary components. So we're going to try to integrate the same things we had before, but over new moduli spaces. So only the space in which we do the integral is different. Formally, the cohomology classes are the same. Now, what's nice here is that when we add boundaries, since there's only one type of boundary puncture, the natural generating function depends on only one more variable, v, that keeps track of the number of boundary punctures. This corresponds to the one parameter I mentioned in the other two approaches, the bare mass in the matrix model for the vector degrees of freedom, and the boundary cosmological constant in Liouville theory. So while the bulk had infinitely many parameters, when you add a boundary, there's only one more boundary variable. Or actually a second one, because you can add another parameter in any of the three approaches to count the number of holes or boundary components. So at least the parameters seem to line up between the different approaches. But at first sight and even at second sight, it looks like the intersection correlation functions or intersection numbers that we want to define in the case of a Riemann surface with boundary don't make any sense. The first problem is that the moduli space of Riemann surfaces with boundary is actually unorientable. So it does not make sense to integrate a differential form in this manifold. And so the would-be correlation functions do not make sense. To understand why the moduli space isn't orientable, let's compare a Riemann surface with a puncture, as drawn on the left, to a Riemann surface with a hole, as drawn on the right, where the circle is the boundary of the hole. Adding a puncture to a Riemann surface adds two real moduli, which we can think of as the real and imaginary part of a parameter, complex parameter x that measures its position in some coordinate system. Adding hole adds three real moduli, which you can think of as the real part of x, the imaginary part of x, and b, where b is the size of the hole, x is still the position. Adding a puncture to a complex Riemann surface does not affect the orientability of its moduli space, because there is no problem in the sign of a two-form dx bar that orients the extra moduli. Similarly, there's no problem if you add one hole because there's no sign problem for the three-form dx bar dB. The problem comes with two or more holes. For punctures, the two forms dx bar are of even degree, and so they commute with each other, so you don't have to decide on an ordering of the punctures in order to orient the moduli space. But for holes, we have instead for each hole a three-form dx bar dB, and these anti-commute for different holes. So for a Riemann surface with more than one hole, to try to orient its moduli space, you'd have to pick an ordering of the holes modulo an even permutation. So because the three forms dx bar dB for different holes don't commute with each other, to get an overall sign, you'd have to know how to order those factors. Of course, you don't completely know how to order them because a pair of transpositions would cancel out, but you do have to know how to order them up to an even permutation. Actually, a Riemann surface with two or more holes will have a diffeomorphism that exchanges two of the holes, and therefore the moduli space of Riemann surfaces with at least two holes is actually unorientable. So that's pretty bad, and that's one reason our correlation functions don't make sense. There's actually a second problem, and the second problem is that although the moduli space of Riemann surfaces with punctures is a manifold, more precisely an orbifold, but it's a manifold or orbifold without boundary, but once you have holes, you're actually talking about a manifold with boundary. I'll try to give a schematic explanation by drawing two pictures. So on the left, I've drawn a closed string degeneration, where as that circle, which is labeled, shrinks down to a point, the two branches of the Riemann surface on the left and right become decoupled. But this happens in complex codimension 1. There's a real parameter, which is the circumference of that circle, but there's also a twist angle, a relative twist between the two sides. So the degeneration of a complex Riemann surface occurs on a complex divisor, which means real codimension 2. It's a complex divisor, not a boundary. On the right, I've tried to indicate an open string degeneration. I'm not sure the picture is terribly clear. Locally, our open Riemann surface with boundary, I've just drawn it on the plane, and you're supposed to think of the colored part of the plane as being our Riemann surface, bounded by the two black curves above and below. And now there's only one real parameter that controls this, which you can think of as the neck of the narrow region where the colored part of the picture becomes very thin, and the two black curves are approaching each other. As they approach each other by adjusting one real parameter, you get a boundary of the moduli space. So the moduli space of Riemann surfaces with holes has boundaries, and that's bad because topologically, without additional information, you can't define intersection numbers on a moduli space with boundaries. So the integral of a cohomology class is well defined on a manifold without boundary, but not on a manifold with boundary, at least unless you're given some sort of trivialization along the boundary. So in the early days of this subject, back around 1990, I was familiar with at least some of these problems, but I couldn't see what to do about them, and eventually gave up and moved on. I was very surprised a couple of years ago when Pandey, Solomon, and Tesler solved these difficulties. The proof was completed by, some of the statements was completed by Buryak and Tesler in another paper. They gave a satisfactory definition of the open string correlation functions of topological gravity. That is, they found an appropriate substitute for the naive idea of integrating over these new moduli spaces, the same cohomology classes we had before. And they showed that their correlation functions satisfy close analogs of all the usual equations satisfied by the more familiar theory for closed Riemann surfaces. So by usual equations, I mean a lot of equations that were studied a lot in the period close to 30 years ago, and which I won't have time to explain today. But anyway, the usual equations include KdV equations, Virasoro constraints, and topological recursion relations, none of which I'll be explaining. But all of which were generalized by the mathematicians from the case of closed surfaces to the case of open surfaces. Now, in a recent paper, Robert Dycraft and I compared their answer to the matrix integral that I described earlier for a Riemann surface with boundary, and we also described their construction in a somewhat more physical language. So that's what I want to tell you about. Well, as a physicist, you could think of the fact that the moduli space in which we want to integrate is unorientable. It's a kind of gravitational anomaly. It means that there is a diffeomorphism of sigma, namely one that exchanges two hulls, that reverses the sign of the integration measure in the path integral, the integration measure we're trying to use in computing correlation functions. So what do you do as a physicist when you run into an anomaly? Well, one option is to add another matter field to cancel the anomaly. Usually we try to compensate for an anomaly by canceling it by adding another matter system. In the present context, though, because we want to get intersection theory, the matter system is going to have to be a two-dimensional topological quantum field theory, so as to not disturb the topological nature of the whole construction. However, this topological field theory has to have the property that it's not just anomaly-free, but actually trivial on an orientable Riemann. Gosh, I wrote orientable Riemann surface, but I meant a Riemann surface without boundary. You see, we want to generalize the theory we already had for Riemann surfaces without boundary to the case of Riemann surfaces with boundary. So when there's no boundary, we don't want to change the theory. So whatever we add is supposed to be trivial if there's no boundary. Yet it's supposed to have an anomaly if there is a boundary. Well, luckily, we don't quite need that. What we really need is that the theory we add should be trivial up to a renormalization of the string coupling constant. So a G-loop amplitude is proportional to the 2G minus 2 power of the string coupling constant, and a renormalization of the string coupling constant would multiply a closed string amplitude in genus G by some constant to the 2G minus 2 power. So a topological field theory that does that is the next best thing to being trivial, because it means that if you compensate by rescaling the string coupling constant by a factor of 1 over c, you'd cancel the effects of this new matter sector. So we want a new matter sector which is trivial in that slightly extended sense if there's no boundary, but that magically develops an anomaly when there is a boundary. In particular, the topological field theory we're looking for must have for its genus G partition function on a Riemann surface without boundary some constant to the 2 minus 2G power. Well, the answer turns out to be in part that the surface must be endowed with a spin structure, though we were studying a problem that doesn't seem to involve spin structures. In 2 dimensions, there's a rather trivial topological field theory in which one simply sums over spin structures, weighting each one by a factor of 1/2. Dividing by 2 is a special case of dividing by the order of the automorphism group. 2 is the number of automorphisms of a spin structure. You can think of this as a discrete version of Fadeev-Popov gauge fixing, where you divide by the volume of the gauge group. In genus G, there are 2 to the 2G spin structures, so if you just count them, weighted by a factor of 1/2, what you'll get is 2 to the 2G minus 1. Well, close but no cigar, this is not of the form of any constant to the 2 minus 2G power. So this theory will not do. There is a slight modification that does work. A spin structure in 2 dimensions can be either even or odd. We'll recall the dimension shortly. We'll recall the definition shortly. There's a topological field theory in which the spin structures are weighted with an extra factor of minus 1 to the W, where W is 0 or 1 for an even or odd spin structure. The partition function is then 1/2. the sum over spin structures of minus 1 to the W of S, where S is a spin structure and W of S measures whether it's even or odd. In genus G, I've indicated the number of even spin structures and the number of odd spin structures. And so if you do this sum, you find that the partition function of this theory is a half of 2 to the 2G, a half of 2 to the G, not 2G. And likely that's the square root of 2 to the 2G minus 2. So we found the theory whose partition function on a genus G surface that has no boundary is trivial in the sense that we can compensate for it by shifting the string coupling constant. However, the theory with this factor included has an anomaly on a Riemann surface with boundary, which is what we want, of course. Well, to see why there's a problem on a Riemann surface with boundary, let's recall first that one definition of W on a Riemann surface without boundary is as follows. View sigma as a complex Riemann surface, and view the spin structure as a square root of the canonical bundle. I'll denote the square root as k to the 1/2, where k is the canonical bundle of sigma. Then you can show that the dimension mod 2 of the space of global homomorphic sections of k to the 1/2 is a deformation invariant, and this is W. One way to prove the deformation invariance is to interpret the d-bar operator on k to the 1/2 as a Dirac operator, and to interpret W as a mod 2 index in the sense of Atiyah and Singer. This definition of W does not make sense if sigma has a boundary, because then we no longer have the chiral Dirac operator whose mod 2 index we were studying. And indeed, there's no way to define W as a topological invariant on a manifold with boundary. However, even if sigma has a boundary, it's possible to define minus 1 to the W as a unit vector in a real line associated with the boundary. That follows by a kind of tautology. You have a surface sigma, well, think of the surface we're interested in as being what's to the right of the red circle. And based on some abstract nonsense that I don't want to explain in too much detail, if you have an invariant, which is minus 1 to the W, of a closed surface, you can define minus 1 to the W as a unit vector in a real line associated to the boundary when there is a boundary. So it's kind of a big tautology. The definite, precise statement isn't very illuminating. But in that generalized sense, you can define minus 1 to the W. Now, what would help in finishing this lecture would be if minus 1 to the W, the fact that minus 1 to the W is non-trivial on the surface with boundary is a kind of anomaly of this topological field theory when we try to formulate it on a manifold with boundary. Minus 1 to the W is no longer well-defined as a real number. It's instead well-defined as a section of a certain real line bundle, and that real line bundle measures the anomaly. So it would be easy to finish this lecture if it were true that the line bundle where the matter system has its anomaly is the same as the line bundle of the gravitational system. Unfortunately, that's not quite true. But just to say what we would have wanted, let's call the orientation bundle of the moduli space capital OR, and that's the real line bundle whose non-triviality expresses the fact that the moduli space is unorientable. So if the matter system had the right anomaly, then I would have simply included a factor of minus 1 to the W in the definition of the quantity that we integrate over the moduli space. Then including that factor minus 1 to the W would have canceled the anomaly. We'd still have to deal with the fact that the moduli space has boundaries. However, it's not quite true that the matter system has the right anomaly. What's true is a little more complicated. And even to state what's true, I have to remind you that a circle, such as a boundary component of sigma, has two possible spin structures, which mathematically are called bounding and unbounding. One is the boundary bit disk, one is not. Physically, they're usually said to be of Neveu-Schwarz or Ramond type, respectively. So we could, in general, say that the boundary of sigma is a union of many circles, some of Neveu-Schwarz type and some of Ramond type. So here, so B is the set of boundary components with a boundary of Neveu-Schwarz type and B tilde for Ramond type. And Si, S prime J are the boundary circles of the two types. Over a circle S with a unbounding spin structure, which is the Ramond case, where the spin bundle is trivial, a trivial real line bundle. So now, in such a case, the Dirac equation on S has a zero mode, and there's a natural real line, epsilon S, which you can think of as the space of zero modes of the Dirac equation on S. So there's a natural real line bundle over S, which is the space of fermion zero modes on S. The correct statement about -1 to the W is not that it takes values in the orientation bundle, but that it takes values in the tensor product of the orientation bundle with the tensor product over all boundary components of what I called epsilon I. Actually, that should be the Z2 graded tensor product, but I won't explain precisely what that statement means right now. Now, then the mathematicians make use of the following lemma. So, or they invoke the following rule in defining their theory. Recall that in one dimension, a spin bundle is a Frank 1. So likely it has up to homotopy two possible trivializations. The rule used by the mathematicians is that away from marked points, the spin bundle of a boundary circle is trivialized. The choice of this trivialization is part of the data we sum over. But the choice of trivialization is required to jump when one crosses a boundary puncture. So in this picture, the Riemann surface of interest is meant to be the green shaded region, and the boundary is drawn in blue at the bottom of the green rectangle. I've also indicated 3 boundary punctures. Those little blue dots, or whatever they are, little blue discs, are meant to be boundary punctures. And away from a boundary puncture, the spin bundle of the boundary is trivialized. It has 2 possible trivializations. And the rule of PST and BT is that the trivialization of the boundary spin bundle changes sign or jumps whenever you cross a boundary puncture. So with this rule, the number of punctures on a circle S with bounding or unbounding spin structure has to be odd or even. Because, for example, let's consider the bounding case. So I've drawn here a disk now. So here are Riemann surfaces of disk. I didn't shade it, with the boundary being the circle. And I've drawn some boundary punctures. I think the number of boundary punctures, 5 boundary punctures. Now, you have to remember that in the case of a bounding spin structure, the spin bundle is a non-trivial real line bundle. So it has no global trivialization. So any attempt to trivialize it will have to allow at least one jump, and more generally an odd number of jumps. So with the rule that away from punctures, the spin bundle of the boundary is trivialized, and the trivialization changes sign when we cross a boundary puncture, it follows that when the circle has a bounding or Neveu-Schwarz spin structure, it must have an odd number of boundary punctures. And conversely, in the Ramond case, where a global trivialization exists, if there are any jumps, there have to be an even number of jumps. I'm not quite sure what's happened, but I've run into a small logistical problem. Okay, fine. Right. Now, as a special case, suppose that there are no boundary punctures at all. Well, if there are no boundary punctures at all, then each boundary component has to be of Ramond type. So, okay, remember, away from a boundary puncture, the spin bundle is trivialized. So if there are no boundary functions, the spin bundles are actually globally trivialized on each boundary component. So each boundary component then has to be of Ramon type, where such a global trivialization on the boundary of the spin bundle is possible. So then, by the PST-BT rule, all the boundaries have unbounding spin structures, and the spin bundles epsilon I of the boundaries are all trivialized. So once a trivialization rho I of the spin bundle of each boundary component is picked, that trivializes what was the discrepancy between the anomaly of the matter system and the gravitational anomaly. So then there's no problem with orientations in defining the correlation function we want to define. It takes a little more work to show, but it turns out that when one includes boundary punctures and one has only piecewise trivializations of boundary spin bundles, and those piecewise trivializations jump across boundary punctures, there's still no problem with orientations. The other problem in defining the correlation functions is also resolved. Recall the other problem is that the moduli space naively is a manifold or orbifold with boundary. But when local trivializations of boundary spin structures are required, the boundaries behave as if they're of real codimension 2. I won't explain how this happens, since I want to use the remaining time to describe the physical interpretation. However, in our paper, Robert Leckert and I do give an introduction to this story about why the boundaries behave as if they're of codimension 2. So the basic approach to a physical interpretation. Let's go back to the fact that on a Riemann surface without boundary, we had a trivial topological field theory. So I'm going to discuss something which is very trivial. It's a Landau-Ginzburg theory with a single chiral superfield and a quadratic superpotential. So if you're familiar at all with the relation of Landau-Ginzburg theories to conformal field theories, you know that the case of a quadratic superpotential is the trivial case, it's the uninteresting case. So if we want to have a bulk theory that's trivial, we take a quadratic superpotential. The superpotential only has one critical point, which moreover is non-degenerate, and that's why the theory is trivial. Since W is quasi-homogeneous, in fact it's even homogeneous, you can make a topological field theory by twisting. After twisting, W is supposed to have spin 1, so since W is quadratic in phi, that means phi has spin a half. And so the twisted theory requires a choice of spin structure, as in the story I've been telling you about by the mathematicians. You can show that on a closed surface signal with a given spin structure, the partition function of this twisted theory is minus 1 to the W. Well, actually half times minus 1 to the W. But anyway, where it comes from is that there's a unique classical solution, phi equals 0, and the sign of the fermion determinant gives the answer minus 1 to the W, and the 1/2 is because a spin bundle has two automorphisms. Now, if we want to study this theory on a Riemann surface with boundary, we need to pick a boundary condition, which means, in a more physical language, we need to pick a brane. Roughly speaking, there's only one natural brane in the problem, which is a Lefschetz thimble associated to the unique critical point at phi equals 0. To be more exact, this Lefschetz thimble is the support of the only natural branes. We have to remember now that, in general, in the A model of the target space X, the choice of a Lagrangian submanifold is not enough to determine a brane. Well, you need various additional data, but the only part of it that will be important for today's lecture is that you need to pick an orientation of L. So I won't mention the things that aren't important, but what is important is that to specify a brane with support L, L has to be oriented. So in our problem, there are two natural branes, B and B prime, which correspond to the same Lefschetz thimble with one or the other orientation. And this Lefschetz thimble is nothing fancy. It's just the locus in which phi is real in the complex phi plane. Neither one of these two branes is more natural than the other, and it turns out that globally you really have to include both of them if you're going to include one. To get the PST-BT answer, that corresponds to the theory with one brane of each type included. And now, in the twisted theory, the branes have a special meaning. So away from the boundary, phi is a section of k sigma to the 1/2. Remember that in the twisted theory, phi develops spin half, which in terms of algebraic geometry means that it's a section of the square root of the canonical bundle of sigma, or in differential geometric language, it's a spinor field in sigma. And now I can tell you what the branes mean in the same language. The branes simply mean that along the boundary, phi is a section of the real spin bundle of the boundary. In bulk, the 2 manifold has a complex spin bundle of rank 1. The boundary has a real spin bundle of rank 1. And the meaning of the brane is simply that phi along the boundary is a spinor of the boundary. Each boundary segment is labeled by B or B prime, corresponding to a choice of orientation of the spin bundle of the boundary. Since the spin bundle of the boundary is a real bundle of rank 1, a choice of its orientation is the same as a trivialization of this spin bundle up to homotopy. And thus we have the PST-BT rule. Away from boundary punctures, the spin bundle of the boundary is trivialized. The rest of their rule says that the trivialization jumps across each puncture. So in physical language, it means that the boundary operators are of type B, B prime, or B prime B, but not of type B, B, or B prime, B prime. This has a simple explanation. The only local BRST invariant operator of type BB or B prime B prime would be a multiple of the identity. And since the one-form descendant of the identity vanishes, a multiple of the identity wouldn't be useful or interesting in this context. So there isn't anything you can do with BB or B prime strings because the appropriate one-form descendant vanishes. So the only boundary insertions that are interesting are the ones of type B, B prime, and I see a misprint. It should be B, B prime, or B prime B. I wrote B, B prime, or B prime, B prime. Moreover, you can show that globally, you cannot distinguish B, B prime from B prime B. So there is essentially only one type of boundary insertion and one boundary coupling parameter, as in the theory of the mathematicians. So that's what I have to offer today, and I hope it's been an interesting introduction to, well, first of all, the difficulty in generalizing two-dimensional topological gravity to Riemann surfaces with boundary, and second, to the methods by which this has actually been achieved. Thank you.